Yeah, hi. Thanks for the great turnout. Really means a lot that you guys come down here to the basement. So I'm going to talk a little bit about replacing engineering work, especially data science work, with compute power. I'm a data scientist, used to be a quant researcher, and for all the data scientists in the room, it's really about replacing yourself with a machine today. A little bit about myself. So I originally studied business, and then took a little detour and taught economics students about machine learning and how to use it in economics and finance. Eventually wrote a book about it. Then decided to study financial economics to get a little bit of a economic understanding of how markets actually work. Then was a contract quant researcher for a big hedge fund, and eventually moved to become a data scientist at Quantum Black. Quantum Black is a consultancy. We help clients with really hard analytics and machine learning problems. We usually deliver a software that they then use to optimize all kinds of things, predict things, super interesting problems, and really all industries. So I've, for instance, recently been working a lot on pharma, which I didn't know much about before, but it's really interesting what you can do there with machine learning. Today's talk is not about a specific project that we did. It's much more about how we data scientists can make our work faster, more reliable, and effectively cheaper. Cool. So if we think about data science, it's really all about optimization in some way or another, right? Either it's very indirect and we provide descriptive analytics which then will help decision makers make more optimal decisions, or it can be really direct when we try to learn the optimal policy directly with reinforcement learning or something like this. And usually it's somewhere in between where we try to predict something, and this prediction is then used downstream by decision makers to make decisions. And usually we are really interested in optimizing that decision metric, which can be really hard because this decision metric is not easily quantifiable, and I'll get to that. On top of that, we have a second kind of problem, namely that our work is really uncertain. We usually don't know upfront if the thing that we're trying to do will actually work or how it will work, which algorithm is the best to choose, which features should we use. So we spend a lot of time on this iteration loop, the famous data science iteration loop. You can spend weeks or months, depending on how important the thing is that you're building, maybe even years, just like getting more incremental improvements. And as much as we like to pretend otherwise, this is really, nobody really knows what they're doing. It's a lot of trial and error, just, maybe this works, and then you do it, and then you're like, oh no, it actually doesn't work. If you're a university, you have grad students, which will do it at a very low cost. If you're a company, then you have to pay really large amounts of money to get it working, which is not great. And we want to make that a lot easier and cheaper. And the problem in this is really the data scientist. So data scientists are expensive. Humans are expensive. They need food. They need a place to live. London is an expensive city. So you have this big cost, and then all the extras like healthcare and stuff. Well, compute is really cheap. Like if you get a preemptible CPU from Google Cloud, it costs you less than a cent an hour. So you maybe really want to think about, hey, how many CPUs do I actually get for one data scientist? And then on top, if you're trying to scale, so oftentimes then people go like, oh, this takes so long. Let's just add a few more data scientists, right? But what then happens is that you create a lot of communication overhead. So suddenly all these people need to talk to each other, and that's actually like an exponential accelerating curve. And you end up with the, no offense, -1x engineer that actually makes your project slower because you now have to do so much talking. Well, with computers, you don't add this extra communication nodes because one person talks to one computer, and even if the computers don't talk to themselves, they don't attend meetings. So that saves you a lot of time on the communication overhead. So given that if you hire a data scientist consultant for maybe $100 an hour, which is not an expensive consultant, you get 18,000 CPUs, and all these people don't talk, all these CPUs don't talk, you maybe want to think really, really hard about if you can swap out some of that data science time with compute time. And that is my topic of today. You might be thinking, cool, problem solved, let's just use like AutoML, like Google AutoML, Databricks AutoML, like every provider these days has some kind of AutoML solution, and for people that haven't used it before, usually boils down to some kind of grid search over the model space, and then you get back the best performing model on your holdout test set. But that's a flawed approach, because just a naive grid search does not know all the things that you already know. It does not know that you might have some constraint in your business case. It might not know that you already know that some of your data is leaky and that you shouldn't rely on this feature too much because it will not be all that predictive in production and it is in your data set, but you cannot really fix it. It doesn't know that you have the need for explainability. It's just like a kind of dumb search. It's so dumb indeed that people have made memes of how like artificial intelligence just optimizes on one metric and doesn't really consider all the other constraints and doesn't really do the critical thinking. So at this point, we can think about, hey, let's kind of split up the work more intelligently. Let's do the computers do what they're good at, which is the mind-numbing experimentation, number crunching, thousands of iterations, and let the humans do what they're good at, which is critical thinking, contextualizing, adding nuance, and then we will get a better outcome. Also, on top of that, it will be much more fun because just numbingly trying things is not really fun. So I call this kind of semi-AutoML. It's a two-step approach. First, you have a machine search over the pipeline space and the model space, the feature selection space. And it returns not only a best model, it returns actually all its trials, and that is a data set that you then as a data scientist can analyze and get ideas from that will then help your actual choice of the perfect model. So you will not just pick the best performing one, you will look at this data set and then figure out, okay, this actually is what we're gonna do. So what we're going to search over, the pipeline space is not only model hyperparameters, it's also things like data cleaning stuff. You can just treat that as another hyperparameter. So if you think about missing values, for instance, there's multiple ways of filling missing values. You might put in some placeholder value like -999, or you might fill it with a mean, or you might do some prediction of what the missing value could be. Usually it's kind of hard to see upfront what the best way is. So you say, okay, this method is just another hyperparameter, and we're going to search over that. Same with feature creation. You might think of like some binning or some interaction features or something. And then again, it's usually hard to see that upfront, and you can just see that as kind of another variable that you search over. Model choice and output post-processing, kind of a little bit more standard. You might want to like find a good threshold of probability when you're doing classification, or you might want to do some sculpting, some normalization of the outputs. So all these kinds of things, you can just treat them as another variable, and you come up with this really high-dimensional search space, which should ideally also include how you go from your model to the business decision. That's often kind of overlooked and then happens sort of ad hoc. That you say, okay, we predict this to happen, but how should we decide on this? Let's make sure that we add that to our search space. So once we've defined kind of what we're after, we will usually need to define some metric, and I'm going to talk about that later because that's a really tricky bit. We need to define which parameters we want to optimize. We should set some priors and sensible restrictions to make sure that we don't end up with something that we don't really want. And then we will run our favorite optimization, and then we will look through the data that results from that. You can do that jointly, so you might want to search over the entire pipeline at once, or you might want to do that for every single step at once. So you might want to just like search for optimal features by itself, and then afterwards search for the model, or you might want to do that together. If you do it separately, that will of course kind of restrict your optimization problem, and you will effectively have an easier task, kind of at the expense that you might not find kind of really interesting feature model interactions or something like this. So if you can and your pipeline is not that big, you might want to do it jointly. Otherwise, if it's a really big pipeline, it might make sense to do it separately, really depending on your use case. A word on the metrics. So optimization metrics are really tricky. And the key constraint is that they, at the end of the day, have to be kind of a single scalar number. You know, you have to say, okay, this model has like an accuracy of 80% and this has 82%, but you cannot really compare it across like a really broad spectrum. You can try to find the Pareto efficient curve of a multi-model optimization problem or something like this. But then you cannot get in all the metrics that you might not be able to articulate numerically. So oftentimes, especially when you work with business stakeholders, they say, oh, we really wanted to do this, that, this. And then you're like, okay, how am I going to put a number on this? Probably not. I know it when I see it. So that kind of makes this multimodal approach difficult. No matter what you do, you will always lose nuance when you try to compress things into numbers. It's just kind of like a kind of loss of compression, and then your metric, of course, might no longer be good once you optimize it. Oftentimes, there's kind of a conflation of causality going on. Humans are really good at all this kind of nuanced, non-quantitative, thinking hard about what would actually be a good solution type of problem. So this is why computers often do so poorly and do overfit, is because they're not good at it. So you need to make sure you bring the human back into the loop and let them do that. Cool. So once you've kind of settled on a metric, the metric should only be kind of a proxy and a guideline, and you should be aware that even if your search maximizes a certain metric, it's not the best result. You still have to kind of look at that. And to illustrate that, I'm going to talk about through a few optimization algorithms and kind of showcase of how the metric comes into play. So believe it or not, my favorite optimization algorithm is random search, because it kind of samples very evenly from the entire space. So it gives you kind of a very good overview of what the performance at different points of your space looks like. If you have a fairly fast running pipeline, then random search is often the way to go. It also runs perfectly in parallel. You can scale it as much as you want. So it's often overlooked. But another one that's really commonly used is genetic algorithms. And genetic algorithms does use a metric. And I really like this GIF here because it shows how the genetic algorithm effectively ends up sampling more from areas where your metric is high. So in areas where your metric says it's good, you will just have more data points from your search. You can later decide that you might not want to pick the point that's really the maximum, but you will sample more in this area so you get more information around the high metric area. And that might be really useful, especially if you're in kind of an exploratory phase. So one example from my previous work is that we had this trading algorithm, it would do much better if you just waited a couple of days to buy. So you got the signal, and days later you would buy it, which is in quant trading kind of the opposite of how it usually works. And we later found out that this couple days delay actually meant there was another event happening, which we didn't have in our original data set. So by sampling closer to an optimal value, you might be able to do some interesting exploration. But this only works kind of for mid-sized parameter spaces, so a few hundred parameters or something. It's good at, not so very good if you have thousands of tens of thousands. In that case, you might actually be interested in going to the extreme of the sampling near the high point approach and building your entire pipeline in a gradient-based fashion. So this is the Alpha Star system from DeepMind. It learns how to play StarCraft. And you can see it's actually a pretty elaborate pipeline, but the interesting thing is that you can take gradients through the entire thing. And there's been a lot of work on making this autograd possible. So there's tools like JAX, which is basically a NumPy replacement, but with autograd. Or you could try to build your entire thing in PyTorch or something. So you can usually make your pipeline quite differentiable. And if you use tools like reinforcement learning or something, you don't even really need a differentiable metric. And if you use stochastic gradient descent or put some noise into the gradients, you can still have the sampling behavior near the high points. So you don't only get the final results, you get the high point, and you can checkpoint a lot, so you really get samples and not just the final output as in regular neural network machine learning. So that is great if you have a lot of parameters. If you have a very slow pipeline, and this is especially true if you try to do joint optimization, then Gaussian process Bayesian optimization is for you. There's this really interesting paper which I want to highlight by DeepMind also, which explains how they did the optimization for AlphaGo of the hyperparameters, where every single run of an AlphaGo training step, of course, will take many, many hours. So they needed to make sure to kind of sample at interesting points. And what the optimization algorithm effectively does, it trades off points where it expects high performance to points where it's uncertain about, and then picks kind of the optimal point to run the next experiment. And that's really great if you have just slow pipelines and need to be really efficient about your sampling. You can also do that for much bigger parameter spaces with a version called TPE, like Tree Parser Estimator. A little bit complicated of how exactly that works, but really easy to use with a library called HyperOpt. So I want to walk through a little example with HyperOpt. HyperOpt is an open source hyperparameter optimization library, but I've used it to optimize entire pipelines, trading strategies, and what have you. It's quite easy to use, even for a humble data scientist. It scales on Spark and MongoDB, and literally just a couple of lines of code will give you what you need. And I think as a data scientist, it's really interesting to combine this kind of search tool together with Jupyter notebooks. So you can work in your Jupyter notebook, and then you define a couple of parameters that you want to be searched over, and then you give it to HyperOpt, and it will run that your notebook many, many times with these parameters, and back you come with your output. Make this a little bit richer. We're gonna show it with classic examples like the Titanic example. A little bit ironic, of course, because Kaggle does have very clear metrics, and you know exactly when you optimize them. But think about what you would do if you wanted to predict this to improve ship safety or something, and you get outside of Kaggle land, and that's a little less safe. Cool. So HyperOpt plus Jupyter notebooks. How do we do this? The first step is we need to take our original experimentation notebook and add a little tag to one cell, which we call parameters, and there we need to define all the parameters that we want to search over. This will later help us to essentially just overwrite these so we know where to write. Then we define our search space in HyperOpt. The search space can be conditional, so there might be certain parameters that we're only interested in tuning when we use a certain kind of model. For instance, when we use a neural network, we want to tune different parameters than when we use a tree-based model. So you can make it conditional and basically as complex as you like. Some of them, of course, run a little better than others, but there's not much of a constraint. And then we use a tool called Scrapbook by Interact to save outputs in our notebook. This again just helps us later when we run this through HyperOpt to know where to read a certain metric back from, because we of course need to read a certain metric. You can also use this to save For instance, like other outputs that are not metrics, for instance, plots or charts, or just other values that you're interested in, and then you can read them all back in a pandas data frame for all your notebooks in a pretty easy fashion. Once we've set it up nicely, we can run our notebook parameterized with Papermill, also from Interact. So Papermill will essentially read one of those parameterized notebooks, swap out all the parameters, and then run it, and then give you back the results through Scrapbook. So Scrapbook then just goes and reads the results and gives you back the parameters. And if you define a little function like this, you can simply plug that into HyperArt. This example, of course, only gives you back the best result, but it's very easy to store then all the results in a database. Or what I usually like to do is I like to save all the trial notebooks that it runs. So if it runs a few thousand trial notebooks, I save them all. And then I can later look at the individual ones, at the individual candidates that I'm interested in, and see the entire notebook, if it has plots or if it has other information that might be quite interesting. Cool, so we've run our optimization, and now we get to the part where we divert from regular AutoML and we do some analysis. So this is just a small example. Imagine we're interested in the optimal tree depth for the decision tree, and we get a plot like this of all of our examples, the accuracy versus the tree depth. And you might see, I'm not sure if I get a pointer here, that around 13 here kind of has the high point in it. So naive AutoML at this point would tell you 13. 13 is the optimal layer depth because this is where you get the best performance. But actually you see that the downward trends kind of starts after 8 or 9. So you as a human can more easily spot this and then say, actually, I want to maybe be a little bit conservative. Actually, I'm more worried about overfitting. I want to have a slightly lower value. And this is the point where kind of the human data scientist comes back in to critically think through this and not just accept the maximum value. Cool. Still, if we run more experiments, we have to worry a lot more about overfitting. We need a much larger holdout validation set. I generally think that the classic 30% holdout validation is too little. Might make sense to rather have it, if you have a big enough data set, to maybe make it 2/3 or something be the holdout validation, because you're gonna want to have multiple holdout validation because you're eventually gonna overfit to one of the holdout validation that you evaluate your metric on. So you need to go to the next one. So you just need to have more of those. You should be really intelligent and stringent about your priors. So if you know that it's kind of unlikely that a value swerves too much from a certain range, you should not let the algorithm search over it, because for some weird reason it might find a little gap where you get really high performance in that area, and that's not really what you want. And of course, if you don't need a parameter, don't search over it. It will just add a lot of compute. You will also need to slightly change the way you do software engineering. Your code now needs to be much more self-contained because it needs to be run automatically at scale. You want to optimize maybe not over the entire data set. If you have a big data set, that just makes it really, really slow. So instead, it's a good idea to do the sampling of the pipeline space over a subset and then get some interesting results from there and then run that out on the bigger pipeline. Kind of vibes with the bigger holdout validation set that you do this kind of thing. And you need to have the right infrastructure, so you should really think about how do you run stuff in parallel. If you run things on pandas a lot, then you might want to think about can we run individual instances on different machines of pandas, or can we move to Spark or something like this to just have much more parallel execution. But when you do all of this, you can get a lot of simplicity gains on the software engineering side. This is my favorite neuroscience paper. It essentially writes about how the brain is really, really complex and hard to understand. But understanding how humans learn is not all that complicated, since reinforcement learning provides kind of a fairly good guide. So if you focus your software engineering around the learning of the good software instead of the good software itself, you get great benefits. You see that a lot when teams build strong neural network architecture, learned architectures. You find that the code itself often is surprisingly short and surprisingly simple. So if you've looked at code bases from DeepMind or OpenAI, you find that for the stuff that they do, they're actually quite short and quite simple. So you get a lot of simplicity gains by focusing on the learning rather than the outcome. And that is kind of the breeze through. And maybe at this point we have some questions if there are any.
Do we have a mic? No, we don't have a mic. If you wouldn't mind repeating the questions.
Yes, yeah, sure. Yeah.
Do we have questions?
Yeah, for me, feature engineering is creating new combinations of concepts is like the biggest blocker. Do you incorporate that part of the process to the automation using those libraries you mentioned?
Yeah, you can. So essentially, you treat the combination of features or any application of the features as a certain operation, and then you can do maybe a genetic algorithm search over a DNA that includes the amount of common applications that you have. So if you look at the NEAT algorithm, it's made for neural architecture search, but it contains this kind of building a DNA of operations that the genetic algorithm then searches over. There's a really interesting implementation. I'm not sure if does that make sense?
Yeah, wait, genetic algorithm over feature engineering, like?
Yeah.
Okay.
So you define your feature engineering as a sequence of operations, right? And you treat that as a DNA, kind of. And then you do a genetic search over this DNA, and at each step, the mutation is taking certain operations in or out. And if you're interested in a kind of an interesting implementation that does that for neural networks, it's called NEAT. But I've also seen it for features being done. And if you want to go one step further, you can use a random forest to then get feature importances, just like a non-standard setting random forest. Get the feature importances from there and assign a mutation budget to features that already do well and mutate them more so you get more out of them. Again, sampling at places that have higher value. But yeah, you can definitely search over that.
Do we have more questions?
Cool.
Okay, please, a big round of thank yous to James. Thank you.